I'm Karen Vosloo, and it's my pleasure to welcome you to this Load Research Chapter presentation by Jan Esterhuysen. We invited Jan to talk to us today to share his insights in the working of the power system and how understanding it helps with designing and implementing small systems and microgrids, as more and more communities are looking to protect themselves against grid interruptions. Jan commissioned generation units 3 and 4 at Kendal Power Station, and he still thinks back how he took responsibility as a young engineer and jealously protected his babies to make sure all went well. So I met Jan decades ago when we were both in the Network Development Planning Group in Eskom, Brackenfell. So Jan has since gained experience in various companies in aspects related to electricity generation and distribution. And in 2008, he created the company Energyneering, which designs and builds power systems. So Jan is a passionate, hands-on, practical engineer, and he thrives on fast-paced action. In fact, he inspired 2 of his 5 children to follow in his electrical engineering footsteps. And Jan, we look forward to learn from you from your vast experience. So over to you, if you can perhaps share your video so we can see you. Thank you. Welcome. Over to you.
Thanks, Karen. Thanks, everyone on the panel. I think for us as engineers, the important thing might be to just make sure that we understand the basics. So I think today that we start from the basics. I think back what happened in South Africa when they first started to generate power. The system was so typical. You have one generator and you want to light up a certain suburb or little town, Kimberley or somewhere there. Now it's relatively easy to do that. You put a controller down and you regulate the speed of the machine, and that gives you your specific frequency. And you put a automatic voltage regulator on the alternator, and there's your voltage coming out of the machine. So it's relatively easy to manage that machine in generating power. The advantage of a generator or a turbine or any rotating power generation equipment that we know, driven by fossil fuel, is the advantage is power on demand. Now, if we have not enough generation capacity, we need to add another machine. And that's exactly what happened in South Africa. They start adding machines. Now, if you have, say, 2 or 3 machines at the same place together, it becomes relatively easy to control these machines. But where the challenge starting to rise is if you start to have, say, more places where you'd start generating power. Typical like in Eskom, you have different power stations. So the only way to keep that power grid healthy is you need to have a common place, and there's national controls, I think at Zimmerpan, and they measure the grid on the 400 kV side. If I remember correctly, I'm not sure if it's changed, but a couple of years ago, it was still at Brits, somewhere in Brits area, they measured that. And then at Duva Power Station, they measured the voltage and the frequency on the 400 kV side. That gives them quite a good indication how healthy the grid is. So if they need more power, or if they see the frequencies start dropping, that's the only indication they have. The frequencies start dropping, they know there's not enough active power available. So it can be a very slow process. So they can even pick up the phone, call a power station and ask them to generate another 200 or 300 megawatt. And then the frequency will stable again. The same with the voltage. If the voltage starts dropping, then they call a power station and request for more excitation on one of the alternators. And more excitation will make that the alternator export more megavars into the system, so they keep the whole thing healthy. So there are only 2 things that they need to really look at is the frequency and the voltage. And with that, they can keep the whole system healthy. And for those of you that might remember, years back at Milner's Vlei in the Cape, there was things like synchro condensers. It was rotating machines with no energy input, no active energy input, but reactive energy input into the system. So then you have typical at Milner's fly, you have a rotating machine, you overexcite it on the excitation, and that produced, say, 200 or 300 or 400 megawatts on the system. It gives you voltage support down in Cape Town, and that was the system. So as time going on, it was more economical, feasible for them to replace that rotating machines with static VAR compensation, subcom, and things like that. Sorry, anyone would, yeah. Now, this system was working for many years nicely. And the main reason why it was working nicely is because you sit with enormous amount of rotating mass. To such an extent that if there's a power station trip and the frequency start dropping a little bit, then a lot of the machines, or a big portion of the rotating machines in South Africa, was directly connected to the grid. Those machines, if it's a pump or a fan, centrifugal pump or fan, frequency and power consumption is to the power of 3 related to each other. So a small drop in frequency actually reduce the total consumption in South Africa to such an extent that you will not even notice the drop in the frequency if we lose 1 unit. So national control can stand up, make coffee, come back, give some power station instruction to add another 200 or 300 megawatt to the system. It's a very slow system. And as time going on, and we start moving away from direct motors, and we start introducing, or the industry starting introducing variable speed drives, we disconnect all the fans, all the pumps from the national grid frequency. So they consume a specific kilowatts, and it not even matter what the Eskom frequency is. So if Eskom have lose that automatic balancing effect of the industry to a great extent, in the same time we start getting rid of rotating machines and start introducing inverter-based power supplies, typical like your solar power supplies. So what we will find now is the grid will become more and more unstable. What will happen is, as the rotating mass started to reduce and we introduce more solar power and wind, both of them is not rotating mass. It not add to the dynamic stability of the system. It actually make it worse. So we can put electronic systems in place to make it work. And the problem there is you need extremely high communication rates. You need to have very high gain control system with a very high order of control system. And that's what we find in our microgrid systems. It's not so easy to keep that system stable. So I specifically refer to bigger systems. So if you have a normal household, it's still easy. If you start growing it and you come, say, 500 kilowatt, maybe 1 megawatt, you can still do it with inverters. But if you go beyond that, it becomes more and more difficult. The reason for that is because you're sitting now might be with 10 or 20 inverters running in parallel. And the only way to keep these inverters in step is you need to have a very high speed communication between all these inverters. It's not like normal rotating machines. You need to control them that the switching is exactly at the same time. And if you have one glitch in your communication, the whole system collapses. Therefore, it's not so easy to get rid of Eskom because Eskom still sit with the rotating mass. And that is typical where we have, say, municipalities that request and say, but what's the possibility for us to move off the grid? The problem is the municipalities is looking maybe just at active power and reactive power, but they not really understand what the effect is of the dynamic stability of the system. And that is where we have find it when we start putting relative big microgrid systems parallel with Eskom is starting to blow Eskom's fuses upstream. And you can measure it with normal meters. You need to measure it in like sub 20 millisecond intervals. And then you find out what happened. Your solar system rely heavily on the Eskom grid to keep it stable. Even if it's battery inverters or normal solar inverters, any inverter-based system that's connected to the Eskom grid rely heavily on the dynamic stability of the grid. Now, interesting enough, is in Europe, they have started to inject pulses of say 50 to 100 megawatt into the national grid in very short pulses of energy, and they measure how quickly the grid changes in frequency. And with that, they determine what the dynamic stability is of the specific grid. And that helps them to decide to reduce the renewable energy and make sure that the grid stays stable. So in the past, national control was sitting and just look at the active power and the reactive power. National control need to start looking in the near future what is the dynamic stability or what is the inertia of the grid. And if the inertia of the grid is not high enough, then the whole thing will collapse. So typically, you have two ways of solving this problem. The one is you can see if you can introduce synthetic inertia. They've tried at different places. The one big thing is the Tesla batteries in southern Austria, where they have, regional specification have said they need to give grid support in creating synthetic inertia. Obviously, that didn't work. The problem is you first need to measure an incident, then you need to react on the incident, and then it's too late because you can trip an inverter in less than 20 milliseconds. If you have a rotating machine or alternator, it gives you far more stability. Now, typical what happens now is if you have a town, you want to take the town total of grid, then the question is, how would you supply dynamic stability to that town? I know there's a couple of towns that was in the news over the past months, and the main problem there is how you keep them stable if you start moving off the Eskom grid. Another thing is that I can like to share with you with our experience is just last week in Pretoria, we have a major problem because it was very cold and then clouds coming over, but it's just like patches of clouds coming over. So we have, on some of our sites, have lost production, 80% of your solar production within 2 seconds. So if you have a system running from solar and within 2 seconds you lose 80% of your production, it's not possible to start up a generator so quickly. It's sometimes difficult to start up a battery so quickly due to the chemical reaction of the battery that need to start producing power. Because you're referring now to like in milliseconds, you need a lot of extra power due to the fluctuation in the energy that you supply from the national grid, from the PV plants. So for us to create a stable grid, and with that I refer typically like a 5 megawatt, 10 megawatt, 100 megawatt, 200 megawatt. The only, at this stage, in my opinion, is the only way is to add inertia to the system. Typical like synchro condensers with flywheel technology. About 6 years ago, the World Bank have luckily come to the rescue of the industry, and they have donated money to Siemens, ABB, Schneider, and a couple of other big companies for them to start creating new products or designing new products to fulfill this market, because the World Bank have said it's important that they make sure at the moment if the world start need these equipment, then it's available in the market. And I was very happy 2 months ago. I've seen that Eskom have placed RFI out for high inertia synchro condensers to stabilize the grid, because I think this is a huge, or that will be a huge problem for Eskom. And the problem will be is you will just stand up one morning and everything is dead, because the dynamic stability and the inertia of the supply side was not enough to keep the whole grid stable. We have started picking up in industry with our microgrids. We have tripping mechanisms or relays in place. And what happened is from February this year, we have started experience rock-off trip, rate of change of frequency. Trips, we have February have 1 trip, March we have say 2, and June, I think June there was about 6 trips. Where Eskom frequency changed more than 0.5 hertz within 1 second. And it is typical for me, red lights start coming up, where Eskom start moving in let's say, might be not red zone, but the yellow zone, where we start experience more and more grid fluctuations, and give us an indication that the total rotating mass, kinetic energy, or is not big enough to keep the whole country stable. So to come back to the first question is, if you have a small town, you want to move them off, you have 2 options. You can go for a nice big battery inverter and take all your renewable energy into a battery, and from there you supply your plant. Out of our experience is the moment if you start moving in paralleling these inverters, that's where your problems start. So might be you can parallel 1 or 2 or 3, but the moment if you go say over 3 or 4 inverters paralleling, you start get a lot of unidentified tripping of the system. The main reason is it's the high-speed communication required between the different inverters. So if you look at that, then you can understand why it will be very difficult if you have a lot of inverter-based inverters that you need to keep 100% aligned over a long distance. So typical, you have an inverter in Northern Cape and other inverter in the Eastern Cape. To keep those 2 inverters electronically in phase become very difficult. With normal alternators, it's very simple, because you're not setting the frequency on the alternator or the existing generation fleet of Eskom. You're not setting a frequency on the turbine, and you're not setting the voltage on the alternator. You're just looking at the active power and reactive power produced by that specific system into the national grid. Now, to do this with an inverter is not so easy, because you need to keep these inverters 100% aligned, because inverters tend to start fighting with each other, and that's where the problems start. Another thing that we have found also in South Africa with our load, compare that with European load, is the amount of pollution that we experience out of the consumer side with equipment that's not up to standards create huge problems for the communication in the dynamic stability of the microgrid systems. This is one thing. And then the other thing is what we've also experienced is typical. Some systems work very nicely in a residential environment. The moment if you take the same design into a commercial design environment or industrial design environment, nothing want to work, because there's too much harmonics, pollution on the network, that create these problems. So I see there's or from my opinion is there's a huge challenge for us, but if we think it right through, we can come up with solutions in taking the entire town from the grid, or a big industry from the grid. And I'm feeling quite comfortable at this stage with the technology available and the equipment available to say take a 200 megawatt mine from the grid and supply it with renewable energy. That this is possible, but then you cannot rely on inverter-based technology. You need to move away from that as your grid forming device. You can have inverter-based technology to supply the energy, the active energy and the reactive energy, but then you need to have rotating mass. This is typical what the Americans have said is there's no substitute for cubic inches. Now in our industry, it becomes more and more clear that there's no substitute for kinetic energy in our industry to keep the grid stable. My portion. So is there anyone have answers or anything?
Now that we've got a little bit of the background, maybe start with saying, well, what happens with all these people that want to put PV on their roof? What should they, how is it going to affect the network? What needs to be taken into consideration, and then maybe from small grow into large? But I think there were a few other people that also wanted to speak. Thanks. Peter, do you want to go ahead?
Great, thanks for the very interesting talk. I just had a question around if you've done any analysis around the additional cost associated with adding different levels of inertia, particularly if it's sort of flywheels and so forth. And because I guess a lot of national energy planning models don't really take that into account when looking at the mix. So it would be very interesting to kind of get a view on what those kind of costs are, and for RP type models to include constraints around a certain amount of inertia that must be in the system, and then have a cost for that must be included in the model.
From our side is maybe I must just give you background where it come from. We was working very closely as a company, working very closely with Schneider, and their R&D, renewable energy R&D facilities in Vancouver in Canada. So the World Bank have contacted them about 5 years ago, 4 or 5 years ago, and request more information, what's going on and what the industry will see the future is going. So at that stage, we have a meeting with the World Bank, and we predict that this will happen. And we couldn't find hardware, we couldn't find equipment that can do that. Luckily now you can see ABB have, Siemens have, a couple of other companies also have in the 200 megawatt upper range of synchro condensers connected with flywheels. So it's typical 3000 RPM flywheel running in a vacuum with the alternator running in hydrogen, typical installation like that. The specific cost of that, I'm not sure, because we're playing in the smaller equipment range. The smallest one available now is a 5 megawatt one from ABB. So unfortunately, a lot of our projects is just smaller than that, typically like 2 megawatt and 1 megawatt. So there we built our own system. And it adds to the cost, but you must remember, it actually reduced a lot on the control system cost, because if you want to control a microgrid system, you have two options. The one option is you need to control it in digitally with a control system with extreme high order, high gain in very short time constants. Now, there you need to go down to reaction times of less than 20 milliseconds, and it becomes very difficult to keep a big system stable if you have this short time periods that you need to operate in. So the only other alternatives is to add kinetic energy, and with that you buy time. So typically you buy time in control systems. So now you can go for a far reduced control system that's very simple, running at a very low order control system with low gain and long time constants. And that actually help you portion of the cost. But this is typical things that you need to add to your network, and you feel it not really add value to your system, but you need to have that, otherwise you will have problems. So my opinion is in Eskom context, and that is out of our own experience, is I will force the IPP providers that they run at the higher DC to AC ratio. The reason for that is what we find is if you run at high DC to AC ratio, you get a far more stable supply from your solar system. Because we're pushing now 180%, and we're going up to 240% DC to AC ratio in total off-grid plants, because it gives us a very stable supply from our solar system. It helps a lot. Another thing is also the rotating mass that you add give you time to react. So if something goes wrong, then at least your equipment have time to sense that, and your equipment have time to counter that. Typically, you have, say, a battery inverters. You can start firing them up. They can start producing power. You can have, say, generators. We have some generators that start up in 300 milliseconds. So you can start a generator within 300 milliseconds. That helps you a lot. Normally, it takes you about 20 seconds to 30 seconds for a generator to start and to synchronize with the system. So you have a lot of secondary benefits that can help you to reduce your expenses on that. But from Eskom's side, I think you should seriously start looking at that, because the problem now is you allow IPP people to connect to your grid, and they just add active power and might be reactive power, but they not add to the dynamic stability of your system. And someone need to pay for that somewhere in the future.
So just one follow-up point to that. So if you find with these high DC to AC ratios, does DC connect, so behind the inverter connected storage, start to help with that as well?
For sure. Then you can start adding storage on that side. That will help you, especially with your duck curve at the end of the day, where you have not such a steep a curve moving over from your day to night power consumption.
Okay, thanks. Wayne, I see your hand is up. Go ahead.
I guess, thank you, Mr. Esterhuysen. It was really interesting. This is more a comment than a question. I know that in your according to the standards in South Africa, you have the anti-islanding protection for embedded generators, and some of them actually work with this rock-off, with a rate of change of frequency. So it's my comment is now that if the Eskom system frequency changes too fast, it's very possible then that you can actually lose some of your renewable plants, and then it will actually make the situation even worse. That's just that's more a comment than a question.
Well, maybe on that one, that's exactly what we start picking up in February. We drop our plants, and then we move instantaneously that megawatts over to Eskom, because we trip our plant on a rock-off. So about 2 weeks ago, I've have a quite in-depth discussion with Dr. Hendrik Helmhuis on that. And he's busy to do his calculations, and he will come back to us. And maybe that will come out in a recommendation that the inverters, that rock offsetting on the inverters might be not so good for Eskom, because it can create quite a huge problem if you have this type of fluctuation in the network, and then suddenly you lose all your renewable power.
Yeah, thanks. Corin, your hand is up. Go ahead.
Maybe just something, Jan, you're talking about the AC to DC to AC ratio. Just for those in the audience that really don't know what you're talking about, maybe just give us a little bit of an explanation what you're talking about, and maybe how it relates to smaller installations, please. Thanks.
Your panels is specify on STC rating. That's standard test conditions. Standard test conditions is at 25 degrees with 1,000 watt solar radiation on that, and that's the nameplate value of the solar panel. So for the IPP companies, they want to create the maximum economical benefit to themselves. So what they do is they size the AC to DC or DC to AC ratio is 1:1. So any power that solar panel will produce, you can convert to AC and feed that into the system. So typical in the Northern Cape, you will find a nice, chilly, cold day in winter time with the sun shining quite severely, and you can have 1,200 watt radiation per square meter. Then the panel will produce a little bit more. But most of the time, the panel actually generate a little bit less. So Eskom give the IPP company or producer, say 200 megawatt, and that's the AC rating of the inverters. But you just use that for maybe 30 days a year, and you just use that for a really short time during the day. So two things happen now is that specific IPP project consume 200 megawatt of your, or not consume, they actually take the license of 200 megawatt, where you can have, say, substantially more power if you have, say, give you a 1:4 ratio on your DC to AC. Now you will have, say, 200 days a year where the system produce maximum power, and also generate that through a longer period during the day. The disadvantage is now you have a little bit steeper curve at the end of the production day, but the advantage is for the same 200 megawatt plant, you produce more kilowatt hours. In South Africa, need kilowatt hours. We need energy. We're not needing maximum capacity anymore. Most of our crisis that we have, we run out of energy. So that will help us in creating, with the same network, it will create more kilowatt hours per day. We have run out of energy capacity.
I've got number 2 in the queue is Nsida from Cape Town. Go ahead, Nsida.
Okay. My question is in line, but sort of hypothetical a little bit. But these microgrids, assume you have a microgrid in close proximity in terms of the inverters or PVs that might be around, maybe some utility scale around as well. My concern is with the microgrid, that microgrid has to provide for the maximum demand in any case. So The issue I have is that what happens under cloud cover. Even though you might have compensators with regards for your inertia, wouldn't cloud cover reduce your output and cause some sort of instability on your microgrid?
The easiest way to solve that problem is you start doing demand control. So typical what we do is we put in a fiber optic network, and that can be over a couple of kilometers. So typical we have a 22 kV line running all over the place with a lot of, say, 100 kVA or 200 kVA transformers. Fiber optic running with that, and with that you can control non-critical load. So that helps you, because that you can control very quickly. And then, as you said, the next thing you will be is you need to have a backup system on the generators, and this is where the problems start, because most of the time a generator takes time to start up. So we have 3 levels there to start up generators. Normal is start and synchronize with your microgrid, take that load on. That will take you about 20 seconds. Then you have an asynchronous alternator system where we can start up within 6 seconds, and then we can start up. It's not a normal way of doing that. The most cost-effective way is to find on your demand side where you can switch off some of your load.
Okay, Jan. So you've said 2 things. So one is to curtail your demand, and then the other thing is to supplement the load by on-site mechanisms with your slow, medium, and fast generation.
Correct, yeah. And batteries.
Could you just explain your very fast generation that is 30 milliseconds or so? What does that look like?
It's 300 milliseconds.
Yeah, 300. Okay.
We've built a couple of these things, and we've imported some of them. We started with a flywheel. It's typical V16 Cummins. The ones that we have done is a V16 Cummins engine with a flywheel, and you close the flywheel. It's like that one was like a 6-ton flywheel spinning at 1,500 RPMs. So you keep the engine oil pressure up, and you keep the temperature up, and you once a day you crank the engine just without starting it, just to make sure all the parts are lubricated. And if you need it, you start that engine within 300 milliseconds. The smallest one that we have built was a 7.5 kVA system. That was for Vodacom. The biggest one is 1.5 megawatt. That is for Telkom.
Okay, thank you. I've got a question from Wayne again. Wayne, go ahead, please.
Yeah, thank you, Marcus. This is another statement more than a question. We were working on a site in Zimbabwe where there are existing diesel generators and a PV plant connected in parallel. It's basically a microgrid, but it's around about 18 megawatts. So it's multiple diesel engines. And what they have there is some AI system that actually takes photos, or it takes a real-time image of the sky, and it predicts the cloud cover. And then they actually can ramp up the generators in anticipation of the cloud cover. So I agree that demand side management is faster, but there's also this as an additional mechanism that can also be used.
It's interesting, Wayne. This is like 3 concepts that's available. The one is with satellite imaging, so we can predict quite accurately solar come through, and then that is on our local server, and if there is a potential risk, we send that information through to the site, and we change the settings on the machines so that the machines start start up at the lower threshold. The other one is, and that worked quite nicely, is take fiber optic, and we're taking, say, 1 or 2 kilometers north, 1 or 2 kilometers east, 1 or 2 kilometers west and south. Put detection, and then we put detection on that, okay. And then that gives you a pre-warning to change the settings on your machine, so that you can start your machine at the lower threshold.
Okay, thank you. Zido, your hand is up. Do you have a further question?
Yeah.
Go ahead, please.
I've seen IEC documents with regards to microgrids, but what I've failed to see is any adoption on the South African context. And then the question is, do we have any of these microgrids functioning in the country? And how did we navigate the regulations and legislation tied to the different municipalities and Eskom, and with regards to the holding of the distribution license in terms of NERSA?
The one portion I can answer, the technical one, is there's more. These things are more in private installations, where typically we have a factory and we supply the factory with, say, 500 kilowatt or 1 megawatt or so. The question, or the portion of the question that's on regulations and NERSA and who's responsible for what, I think there's some more experts that can give us advice. It seems to me Karen's hand is up. Seems to me she's more interesting to answer that question, because I believe there's people that's more in that type of business that can give us more clarity on that.
Karen, if your hand's up and you've got something, go ahead.
Yes, unfortunately, it's not in connection with that, Jan. It's I don't have information about that, but I had 2 other little elements which I'd like you to just touch on as well. If I can just go ahead with that, the one is, why is the limit that, for instance, if you want to connect PV or whatever, you're only allowed up to 75% of your maximum demand. So if you can touch on that. And then also if you can just touch on the importance of first trying to sort out the real energy usage of the client before you start just slapping on a microgrid or slapping on new generation, so that you have a proper look at the usage of the energy inside that site. Thank you. That's what I'd like you to just cover. Thanks.
Okay. Try the just Karen, sorry, just the first one.
Okay, the first one was, the limit that you're not allowed to 75%. Install more than thanks.
My personal opinion, I'm not sure where it come from. I think it was a scientific thumbs up for someone, but there's good value in that. Problem is, if you consume power from Eskom, say you have a 1 megawatt feed and your factory use 1 megawatt, and you supplement that with 1 megawatt of solar, then there's no power coming from Eskom. Now, the problem is most of, actually all the control systems that's available in the market is far too slow to cater for that. And we have actually discovered that as we start moving from grid tie systems to microgrid systems, and we realize the available systems in the market to control solar systems is not fast enough. So typically you will have a 1 megawatt PV plant producing 1 megawatt, and now suddenly your load trip. You push that 1 megawatt back into Eskom system. Now your Eskom people will give me maybe advice here. The way I understand it, that I was more on the 400 to 132 kV side. Now, typical what will happen there is you will have online tap changer with, say, might be end-of-line compensation. Now suddenly this changed, and you must remember you just changed the active power suddenly. So you change the active power, so reactive power will still be there, and that will have a huge implication on the Eskom network. So even 75%, I will say, is high, especially if you have a specific area feeding from the same substation, from the same transmission substation. It can be catastrophic for Eskom if you sit permanent with 75% produced by solar and you have this abrupt changing of energy in a couple of milliseconds. The whole thing swing from one side to the other side. The control side, it will become problematic for Eskom. We have, and that's why we have picked it up, we have blown Eskom fuses, upstream fuses, because of this. And then we're actually starting to realize we need to change the whole control philosophy of our systems, and especially for microgrid, because if you have a microgrid system, you sit, say, might be you have a generator parallel with a solar system, suddenly you push back 100% of your available power back into the generator. That generator, not really like it, That's a 75%. And then on your question on the demand side, just to give you indication, yes, we have one of our clients have a milk factory, and they milk cows also, and they produce cheese and all this other stuff. And they have an ice bank, and they build up ice during daytime, and they use it for the milking session tonight, and then build up ice through the night and for the next morning. The price of the ice storage facility is about 250,000 Rand. If we want to build up ice during daytime and we have double the capacity, we can use half of the ice tonight and the other half we can use tomorrow. So it costs us 250,000 Rand to replace or to add that extra facility. If we want to add batteries to do this, it will cost us 1.2 million Rand to do the same. So most of the time, if you can adopt your consuming patterns, your saving is substantially more than it will cost you by supplying battery power or diesel or anything else. So I think it's a whole mind shift that the industry and the people need to go with, and starting to understand, putting it maybe for your home, put a bigger geyser on it, because it's much cheaper to store hot water than to store a battery. It's much cheaper to store ice than to run a fridge during nighttime. So I think the whole thing on the demand side is actually the most important thing that we need to give attention to.
Jan, thanks. It's interesting that you're saying that there are many types of battery, and we tend to fixate on the electrical only. And it's really about where we can get the energy from and the least cost at the time it's required. When you're talking about synchronous condensers on the system, is there some sort of a rule of thumb? As you were talking, I was wondering how much synchronous condenser do we need in our system? How much do we have, and how much is it going to cost to get the balance? Is there some sort of rule of thumb of ratios that is out there right now?
I think it will be difficult to determine that, because what we find in our smaller systems is we work it out on the inertia is kilogram at a specific speed. We work out how many joules we can store within a certain frequency variation. So with Eskom, we as a country, or Eskom, need to decide within what limits, what rock-off is acceptable. Will it be acceptable to have 1 hertz change per second for 2 consecutive seconds? Or what will be acceptable for the South African grid and also the South African consumer. And then you work from there, you work backwards. The next thing will be is how quickly can you add generation capacity? Because if you can add, that initial change in frequency, that's where your inertia will help you. That's within the first second or 2 seconds. Now, after that, you need to add generation capacity. Because if you start, and I've done that calculations just on a high level to see how many motors driving are used for fans and pumps in South Africa. You know, if you reduce the frequency, that will give you a reduction in energy consumption because it's directly connected to the grid. So now people want to save money, they want to be more effective, and they changed that to variable speed drives. So you lost that built-in dynamic stability of your system. So to cater for that, Eskom need to put their dynamic stability in the system with flywheels. The next thing is how quickly can you catch, or how quickly you need to catch that, because it's two scenarios. The one would be is if you can disconnect all your load, that did not help you with your energy that you need to keep the grid healthy. So if we lost 1 unit of Eskom, you lose, say, 800 megawatt, then the grid will slow down, and the fact that the frequency dropping reduce the energy demand. And you find a nice new place where you get stability. The problem is, if you're not getting stability and you drop further and further, how quickly can you bring in energy to catch that and to pull you up again? And that's the concern. Now the problem is with Eskom is we will never, or it will be difficult to install that amount of batteries. It will be better for us to put, say, hydro in and pump storage. Pump storage take time to get the whole thing up and running. And you need to store that in somewhere. That will be in kinetic energy. But to store all that energy into kinetic it will not be cost effective. So it will be good in South Africa context that we also start looking on the demand side, where we actually give people for certain loads that we can quickly drop if the frequency fluctuate too much without creating an unstable grid for us. So I think it's difficult to determine exactly how big that would be. At this stage, we calculate, it depends on the load, we calculate full load 12 seconds from our flywheel with a frequency change of 5 hertz, 2.5 hertz plus and 2.5 hertz minus. And you need quite big flywheels.
Jan, would you say that the way to manage this is that renewable systems that want to connect to the grid must bring their own inertia? Is that the way that this could be managed?
Well, that happened in the rest of the world. That's exactly what they do. They force you to do that. So typical, I will say, is, well, you can just take a normal power station from like Kindle, 686 megawatt per unit, go and calculate what that is, and tell the guy, if you want to produce 686 megawatt, you need to add so much inertia. Then at least you know it will work. And it's not necessary to make too much calculations, because the problem with your simulations that you will have, I assume Eskom use no power factor, you're not using PSSE anymore. So you can do that calculations with that, but the problem is what parameters are you feeding in? What limits are you feeding in? So I will say for start, that will be the right thing. And it's relative. You can just go and look at the spec sheets of a turbine alternator combination, 600 and I will take a normal steam turbine and work out what the inertia is and force the guy to do that. It's
Okay,
part of
thank
his
you.
capital cost of the project.
Yes, but it means that it's a sizable renewable system comes with some overhead, which is a grid responsibility issue. Corin, you've got a comment?
Yes, to tie into that, sort of everyone's talking about the cost of the kilowatt hours is so much cheaper for renewables, but then who pays for the rest needed for the grid stability? And I think if we start insisting on bringing in your own inertia, you're perhaps helping with that. Otherwise, it's the network like Eskom at the moment that needs to foot that bill, and who is really paying for it, and what else needs to be brought online with the cost of buying that kilowatt hours from renewables. So I don't know if you want to comment on that, Jan, because I mean, if those groups don't bring in their own inertia to help, I mean, what else is there in the network that needs to be provided, and who pays for it?
I think, Corin, the thing that we need to flag is in the past, we have two modalities to control. The one is active power and the other one was reactive power. Or real power or imaginary power, if we go to maths, or but I think we all understand that. One, you're looking at the frequency, and the other one, you look at the voltage. If the voltage start dropping on the 400 kV lines, then you know you need to add more reactive power, and you can do that by capacitors or with synchro condensers or whatever. But as I've said, the elephant in the room is dynamic grid stability for Eskom, and that becomes the third component that national control need to look at the dynamic stability of the grid. And that will be a very difficult thing to look at it, because it's quite instantaneous. If you drop hard, and it will instantaneous. It will, you can do virtually nothing. It's not like you see the voltage start fading away and you can phone a power station to react to that. You cannot automate your turbines too much, because that can also create grid stability, because say the one turbine see the grid is start falling and then it react on its own to produce more power. Other ones start pulling back and then these things start fighting with each other. You don't want that, So you want to have that grid stability, and you have one of two options. The one option is you said, no, we want to control it with very high speed electronics all over the country, where we can, if we see we need more, and then it becomes like synthetic inertia. Synthetic inertia is very difficult because it's reactive. The incident first need to happen, and then you have 20 milliseconds to measure there was an incident, or might be 40, or might be even more than that. So you have a couple of milliseconds to realize there's a problem coming, and then after that you might be another second to start doing action. And then you sit with mechanical reaction and mechanical inertia. Things need to start moving to counter this. And it will become a control nightmare, and you will have on a continuous basis have blackouts with the whole thing collapse. So the other way of doing it is to buy stability, and you buy stability through system inertia, through flywheels, through whatever, synchro condensers with flywheel. Then you have two things. You have a synchro condenser you can do VAR control, you can do grid support, you can do, and you have dynamic stability. The only risk that you will set there is, especially if you have transmission lines that's not strong enough, that your fault levels is relatively low at the end of the transmission line, and if I want to put a solar system there, then you can have sub-frequency resonance between your flywheel system and the Eskom system. But I think you can put damping in there and control systems to cater for that. That's the same thing with Kuiberg. I think Kuiberg is something like 6.4 hertz sub-frequency resonant with the rest of the country, and Eskom is aware of that frequency and check it out and make sure that they not operate Kuiberg within that sub-frequency resonant bands, and then everything worked nicely.
Yeah.
In that vein, it sounds as if you're just talking mainly about the bigger systems and the bigger things that Eskom must look at. But now, if you bring it back to the smaller communities that are thinking of organizing themselves into little small microgrids and so on, it sounds, from your experience, you bringing those things into those smaller communities as well, don't you?
Correct,
Not
yeah.
just the bigger stuff.
I think there you have two options. The one option is you put up a plant where you can control the production and you can control the supply to the load. Now, typical up to say 1, might be 2 megawatt systems, there's inverters available that you can supply, say 2 megawatt from a dual inverter system, might be up to 5 megawatt. Advantage now is you produce on one place, you produce the solar, you can control it very quickly, and you have your battery storage, and you produce the power, you step it up, and you go into town with 22 kV, and you supply it with power. That is a relative easy way in doing that. If the community want to become part of that, and the community said, no, they just want to, that's a different model. The community said, no, they want to produce the power on the roofs, and they feed it into the system, and then you need to absorb that power somewhere with a community-based battery. And if the community cannot produce power anymore, then the battery will supply the town with power during nighttime. So you can work out a system where you pay the community for the electricity that the council receive, and then tonight they need to pay more for the battery power coming from the battery. That you can also do the same way. But if you start going a little bit too big, then again your dynamic stability will become starting a problem. Then I will seriously consider putting in a synchro condenser there. It's a mechanical thing, a little bit more maintenance, but it gives you a very stable environment, because now you have, say, 1,000 small solar inverters that produce power, pushing it into the system, and you cannot really control that so nicely as you have it more centralized installed. And it's typical like Cape Town. If you want to take Cape Town from the Eskom grid, you will sit with that problem. You need to seriously start looking at how you will add a lot of inertia to the Cape Town network and making sure it stays stable, and then everyone can start producing power, feeding into the system. The excess power you can use to pump water up to Steenbras and put it in batteries or store it or make hydrogen with it or whatever you want to do it with it. But then you have a stable system. So to summarize, that is out of tests that we have done with GE and Switzerland on different size of inverters. The moment if you start adding more than in Europe, you can add up to 6 inverters and it still works. In South Africa, might be 3 inverters. But most probably 2 inverters due to the pollution, network pollution in the consumer side.
Okay.
And this is purely out of experience. The moment if we have parallel more than 2 inverters parallel, might be it work, and then suddenly it starts falling over on a regular basis. Then somewhere someone have done something, and it's very difficult to find that because there's not regulations, such good regulation on equipment that we bring into the country.
Okay. But okay, let's bring it back now to, people just here, they can put PV on their roof and they can feed back into Eskom. But obviously will create issues and problems as well. But the public doesn't really always understand it. So what kind of issues do you foresee? Will everyone just, feeds in during the day into the Eskom system, but you don't have the bigger microgrid control over that?
Correct, yeah. Well, it's the same that happened now. Is the more load shedding we have, the more batteries people buy, and they buy batteries and they discharge it during load shedding cycle, and the next cycle, if there's power, then they charge the batteries. So we're fighting against each other. Eskom fight with the rest of the country, and we've imported, I think the battery imported double every 3 months now. So every 3 months we import double the amount of batteries as the previous 3 months. People is not putting solar on the roof, nothing, just putting batteries in. Because you charge the batteries. So the more people buying batteries, the higher the load shedding will be.
Yes, but now if you take it that step further, where people decide, okay, they've got the PV now and they've put big panels on their roof, and they're now going to be paid for the PV energy active, that they're pushing back into the system. So it's probably not very realistic for people to think that way, but that's what they think. They think it's going to bring them money to connect to the system.
From a technical point of view, there's not much of a problem of that. It can work nicely because you sit with a nice stable grid. So every kilowatt hour energy that you can put on the grid will help Eskom to pump water for nighttime. The only problem there will come is now people will be incentivized to putting bigger solar on it, and you will sit with your duck curve at 4 o'clock, 5 o'clock at night. So now suddenly you need to have huge take up. Someone need to produce that power. So that's where the utility debt spiral come from, because Eskom need to run the power stations, and then as time going on, they cannot sell the power because they just sell power at night time. So Eskom, and I know Eskom is busy to look at the tariff structure around that. 60% of your cost will be fixed cost, and your energy cost will be 40% of the total bill. So Eskom is looking at that from a macro point of view, not from homeowners so much, because I think due to political reasons, it's not possible for them to change the house structure, tariff structure too much. But Con, that's more like case to case, how much you can feed in, not feed in. I think if people work together and you know how to save money during, maybe I must rephrase it. The problem is if you look at the consumer, and you go back to Dr. Ron Herman's research that they have done at the University of Stellenbosch a couple of years ago, we measure a lot of houses, like thousands of houses, and he drew up the Ron Herman distribution. Eskom used that. You get a typical profile for a household, and you use virtually minimum energy during daytime. All your energy you use basically from 5 o'clock to 8 o'clock, 9 o'clock at night. And you install a solar system, you waste if you put big panels on your roof, except if your battery is big enough to consume that energy. If your battery is not big enough, you waste. Now, that waste you can feed back into Eskom. The problem is you start using power at 5 o'clock at night, and you lost your production capacity at your home. So you can just think what severe pressure that put on the network, on the electrical network of the town, the local network.
Jan, 2 questions from my side. You pointed out installation issues as a factor, and you said there were 2 problems that you ran into with installations. So one is that the equipment is not up to standard, and then the same solution doesn't work in residential and commercial areas because of pollution and harmonics and so on. Do we have a problem with standards in South Africa right now that cover this kind of thing? Or is it still early days and the standards are coming?
And now for you people, the colleagues that's still with Eskom, it will be difficult to hear that. I've taken a couple of people to an installation where it's a private initiative out of the 80s where they've get permission from Eskom to buy in bulk from Eskom and sell it to farmers. They've got 300 farmers on their network. And we've looked at it and said, but okay, what's the possibility in creating similar things like this? And it's scary, but the common feeling, and that is the common feeling on the ground where we operate, on the normal clients and also might be lawyers, it's easy to ask for forgiveness than permission. Just continue and do it, you know. So the problem there is the anarchy that the country has fallen in so wide at this stage that people bring stuff in, they do what they want. And they even broke laws, and they will supply power to whoever want power without just you know. And I know there is institutions, what they call them, these institutions that do everything for the society. They are willing to sponsor money if you need to fight in a court. They said, well, Eskom cannot supply us with power, so we do what we want, you know. Problem. The issue that I'm referring to on the equipment was more the availability of equipment, on bigger size equipment, like your kinetic. Although you start finding technical detail on that, the availability of the equipment still have a very long lead time because they just manufacture it as and when you need that. And that is a problem. I think it will take another 5 to 10 years before you will have it more available so that you can go and buy something from the shelf. And then on the residential side, what they're referring to there is a typical what we find in industrial environment. You will have, say, might be a severely unbalanced load. You will have inertia in your system. Where on a residential, normally you have minimum inertia in your system. So some of these systems work on a basis through control on the frequency. So typical, if the main inverter want more power, the inverter will increase the frequency a little bit, and that signs or reduce the frequency a little bit, and that signs to the other inverters we need to produce more power. And to the other side also, the main inverter need to slow down a little bit, and then it need to accelerate the frequency a little bit. Now, in a lab, it worked nicely. In a residential, it worked nicely. In offices, it worked nicely. You go and put that industrial area where you sit with a lot of inertia and motors, system didn't want to work, So this is the type of things that you as an engineer, you normally think, oh, it will work X, Y, Z. In real life, might be you have a couple of surprises and it didn't want to. And I find even for us, it is quite a couple of times that we overlook at things, They refer to that as school money.
Yes, the difference between gut feel and experience.
Yeah.
I'm hearing that we have an issue then with policing of standards, and but not so much the standards that we require. Would you agree with that?
Yeah.
Okay.
Yeah.
So that is a huge issue. That is it from my side. We have a question from Naniki. Naniki, if you want to ask this question, please come on now, or I can voice it for you. Standing by.
Thank you. Yes, I wanted to get the opinion of Jan. Thank you for the inputs thus far. I just wanted to check your understanding and thoughts in terms of grid forming inverters. I've heard and appreciate obviously the inputs around synchronous condensers and just the impact on inertia on the system. But with regards to grid forming inverters and the development of that technology and applicability in our South African grid?
It worked nicely, but as long as you can keep it one or maximum two inverters in parallel, it works. Because if you look at the way these inverters work, it's typical you have IGBTs switching at 20 kilohertz. And what happened in real life is some might be harmonics on the system, or some of the equipment is not working nicely and they induce currents in the earthing system or whatever. That affect the communication between the two inverters. Now the one inverter fired the IGBT bridge and the other inverter didn't fire it. And those things are quite sensitive to this, and now the whole thing collapsed. And that happened. We have some of these inverters that was running for 3 years. It was 3 inverters running 3 years, no problem. Then suddenly start falling over 3, 4, 5 times a day. Couldn't figure out where the problem is. So we even fly experts from Germany, come work through the whole thing. We couldn't solve the problem. We pack up all these inverters back in a container, ship them back to Germany. We put them up in their own labs there, test through everything, couldn't find any problem there. So they sent us new inverters, so we installed the new inverters. Didn't want to work. And it's typical communication problems because you need very high speed communication between the inverters to make it work. And that's the reason why you can, the first question you ask a supplier, how many of these inverters we can parallel? And then they're starting 10, but just make it 6, And that's typical what happened. And that is the risk that we run. So if you typically have a town and you want to run it, say 10 megawatt with grid forming inverters, if you have big enough inverters and you put them very close at one spot, not apart, you make sure your electromagnetic compatibility is like next level. Your earthing system need to be 100% correct. Your transformers need to be 100% sorted out the way you earth. That might be screening windings between the primary and secondary windings of your transformer. If you tick all these boxes, you can try it. But be careful.
Thank you. I have one last question. I'm looking for hands after that. From your discussion, it seemed like we had a shortage of dispatchable, sheddable load in South Africa, either directly or indirectly through aggregators, stuff that that can be lifted from the network quickly. Would you agree with that? And do you have any idea of how much of our current load is actually under control and sheddable, other than by islanding and those kinds of ideas, basically cutting the entire load base off the grid for certain areas? Thanks.
Marcus, if I take it how difficult it is for us to have a total off-grid microgrid supplying a client with a typical day-night profile, what the extra cost associated to produce power at night time, the extra maintenance cost, the extra control, you name it. So if you have a installation like this, and I see how difficult it is for us to produce power at night time and what the cost attached to that, it becomes difficult for me to see how you can take the entire South Africa from rotating machines and just with renewable power, because the quality of the supply between these two sources is like day and night. There's nothing. Dispatchable power is king, and renewable energy can supply you energy during daytime, but energy and dispatchable power is two different things. So you actually need to invest enormous amount on storage, and with storage you need to put things in like I will say your pump schemes. It's number one. Then after that might be gravitational storage from a mountain down if you cannot do it with pump storage. And then after that you would seriously start looking at things like liquid air storage, this type of plants that you need to store. I cannot see with batteries how you can make it, because the amount of energy you need to store at night time just become too much. We have some clients that use, say during daytime, 600 kilowatt. At night time they use about 20 kilowatt just for the lights. That is easy. But the moment if it's the other way around, where you need a lot of power during night time, it becomes very difficult and very expensive. And I cannot, to be honest with you, I cannot see how we will make it as a country.
Okay, that is a very dire note to end on. I'm hoping for some other hands up where we can get a more cheerful question. Karen, go ahead, please.
Not a question, just a comment and a great thank you to Jan, because I think you've highlighted a lot of things which people seem to skim over and not realize the importance. It's easy for people to think, oh, well, we just put PV on the roofs and why block that? Just do that. And for a small group, just group together and get yourselves organized into a little microgrid. That's easy. But I think you've highlighted it's not as easy as it initially looks. So thank you very much for your time, Jan.
Marcus, maybe I must add that also. When we have commissioned Kendall, while we was busy to commission Unit 3, Unit 1 was running 400 days without a trip, non-stop. So it produced 600 megawatt plus, 24/7, non-stop, never trip once. That is reliability. Some of the kinetic storage units that we've put in 24 years ago, they run for 10 years without a trip, non-stop. 10 years, we stop them, we do preventive maintenance on them, put new bearings in, start them up, they run another 10 years, and they've just 3 years ago redo them all again, and they go for 30 years now. the same piece of equipment. Even on the batteries that we have installed, there's a lot of electronics, a lot of things that can go wrong, and it will go wrong. And we're tripping on like 13 millivolts difference between two batteries, and the whole thing trip, And the problem that we sit with in South Africa, there's no skills to solve that problems. And that's the whole Africa. There's not skills to solve the problem. Even the OEM manufacturers of the batteries, they cannot solve the problems.
Well, Jan, that is, that is hopefully a space, a challenge that we'll meet in the future, simply because it's critical for South Africa. Okay, I'm looking for any more hands. Is there any more questions from audience? Okay, Jan, at the moment we have no more hands. It's my duty to thank you very much for presenting to us today. I think it's been an eye-opener, and you've included some fairly stern warnings for South Africa and how we proceed. As us as members of Load Research Chapter, recognizing this, let's go ahead and try to make it happen. Okay, Jan, thank you so much, and thank you, Karen, for organizing this, and thank you to the 50-something people that came online, and the comments that have been received. Much appreciated. I will close now.
Thank you
Jan,
so much.
once again, thanks so much. Cheers then.
Thanks. Bye.
Bye.
Thanks, Jan.